JMD webinar on the special issue around datasets in engineering design. This webinar is being organized by me, Faiz Ahmed, and Dr. Stefan Menzel, who is here, and Dr. Ikjin Lee, who could not make it today. And I want to thank all the organizers as well as all the speakers who will be presenting their work today about various different types of engineering design data sets. Now I would want to welcome Dr. Namu Khan. Please.
Hello, everyone. My name is Namu Kang, and I'm excited to present our work titled DeepJEB 3D Deep Learning-Based Synthetic JEB Engine Bracket Dataset. This research was a collaborative effort between Narnia Labs and KAIST Smart Design Lab. Here is the outline for today's presentation. I will start with the background, explaining the motivation for our work. Next, I will introduce how we generated the data set, followed by how we performed the dataset validation. Finally, I will conclude with the key takeaways of our research. Let's begin with the core challenge that motivated our study, data scarcity in engineering. As the chart shows, compared to the field like NLP, computer vision, which have massive data sets, the engineering domain suffers from a lack of large-scale, high-quality data. For instance, the SimJEB dataset, a well-known benchmark for jet engine bracket, contains only 381 samples. This limited size poses significant challenges for developing and testing robust engineering AI models. To address this bottleneck, we developed DeepJEB, a large-scale synthetic dataset. Our solution is a comprehensive data generation workflow, which I will explain in detail. Through this fully automated pipeline, we created a dataset that is 5.6 times larger than the original SimJEB dataset. It is not just larger, it also richer, containing over 209K detailed node-level data points per sample on average. Now let's dive into the specifics of our dataset generation process. The process begins with step 1, seed data selection. We started with the 381 samples from SimJEB and filtered them to ensure quality and consistency. We removed about 100 samples that had geometric issues, such as internal cavities or boundary alignment errors, which could cause instability in the simulation pipeline. This left us with 263 high-quality CAD models to serve as the seed for our generative process. In step 2, shape generation, we employed an implicit neural representation model, especially on autodecoder architecture of the SDF. This allowed us to generate about 4,800 new diverse bracket designs by interpolating in the learned latent space. However, generative models can sometimes produce irregular geometries. Therefore, step 3 was shape filtering. We identified and removed about 2,000 geometries that are torn or had disconnected regions, ensuring they were physically viable for analysis. And this resulted in 2,700 well-formed shapes. Next, in step 4, FEM simulation, we established a fully automated pipeline to label the engineering performance of these shapes. We perform 4 linear static load cases: vertical, horizontal, diagonal, and torsional, as well as modal analysis to find natural frequencies. This automated process wasn't perfect, so we encountered about 200 simulation failures. Furthermore, in step 5, outlier removal, we filtered out about 400 samples with unrealistic stress values caused by mesh artifacts. And after that entire rigorous process, we finalized the DeepJEB data set with 2,138 samples. And here is the result, the DeepJEB data set. This gallery showcases the diversity of the generated brackets. DeepJEB provided far more than just geometry. For data quality, we used second-order tetrahedral elements for higher precision, resulting in an average of 130,000 elements and over 209,000 nodes per sample. The data categories is extensive. We provide geometric data like step and SDL files, scalar data such as mass and maximum stress, detailed field data for every node. Even rendered the image from 26 different views to support research on multi-view models. Now I will discuss how we perform the dataset validation to ensure its quality and comprehensiveness. Our quality assurance had two parts. First, for performance data verification, we identified and removed the simulation outliers using the IQR method. The initial data set shown in plot A had a long tail of unrealistic stress values. After filtering, plot B shows a much more uniform and reliable distribution. Second, for geometrical feasibility, we ensure the final mesh quality was high. We checked the metrics like the aspect ratio and find that only about 1% of mesh elements exceed the recommended threshold for stress analysis, confirming the data set's integrity. And next, we performed the diversity check. To visualize and compare the design diversity, we used beta VA to reduce the dimensionality of the shape into a latent space. This scatter plot clearly shows the latent space for both data sets. The dark orange point represents the original SIMJAP samples, while the light orange points are from our DeepJEB data set. And it's evident that DeepJEB provides an expanded, denser, and more diverse design space, which is crucial for training more generalizable AI models. To demonstrate the practical value for DeepJEB, we conducted a case study on surrogate modeling. We trained the surrogate model to predict structural performance based on the 3D shape. When trained on DeepJEB, our model achieved average R-square of 0.967, 3.2% improvement over the model trained on SIMJAP. Furthermore, MAP was reduced by a massive 72.3%. These results powerfully demonstrate the superior quality and utility of our synthetic dataset. This brings me to the conclusion of my presentation. In conclusion, the DeepJEB dataset addresses the critical issue of data scarcity in engineering. It is 5.6 times larger than SIMJAP dataset and provide more accurate and comprehensive data. And as a result, DeepJEB is already being used in the research for tasks like surrogate modeling and design optimization. So it is well positioned to become a standard benchmark for evaluating engineering AI models, opening up new research area like generative AI. The potential applications are extensive. With DeepJEB, we can implement AI-driven design process. Let's take a look at the video. You can generate thousands of concept designs, and you can explore generative design and predict the engineering performance in real time. Or you can cluster them according to the design similarity. You can filter them. You can compare your design with the data. And if you input our target performance, you can get optimized design by generative AI. Or you can share the good design with your team members. And finally, you can interpolate new design between the good design candidates. Thank you very much. Thank you for listening. And DeepJEB dataset is accessible through this QR code and URL.
Thank you, Namu.